Okay, good day to everyone. We're already finished discussing the two kinds of DC generators. So we have the separately excited generators and the self-excited generators. So in the separately excited generators, we need to consider another source of DC voltage, say another DC generator or a battery to excite the field windings. While for the self-excited generators, we're going to utilize now the output of the armature. So no need to consider another source of DC voltage. But there's a problem in the self-excited generator. So there is a tendency that it will not build up its voltage if we could not meet the different conditions for a self-excited generator. So we will discuss here the conditions in a certain generator in order to build up voltage. So let's try to consider a shunt generator here. Okay, so voltage build up of a self-excited shunt generator. So number one condition is the machine must develop a small voltage resulting from residual magnetism. Because if there is no residual magnetism, usually it could not generate voltage or it could not build up voltage. Why? Because if we have, say to illustrate that, so let's say to consider a two-poles machine. So this source of magnetic lasso force is made up of a electromagnet. So if there's no residual magnetism, so if the current that is applied to the field winding is zero, then the flux produced is also equal to zero. So assuming the field current IF is equal to zero and there's no residual magnetism. So even we're going to rotate a conductor and there is no flux that is cut by this conductor, therefore it will not generate any voltage. And so if there is a small amount of magnetic loss of force due to residual magnetism, so that small amount of voltage, that small amount of flux that is cut by the armature winding will produce a small amount of voltage. It is called as the residual voltage. So that residual voltage is due to residual magnetism. And from that, if we have already generated a small amount of voltage, that is applied again to the field winding based from the schematic diagram of a shunt generator like this. So if we have already a residual voltage as our output at that instance, this AR now is applied to the shunt field, causing now to have a field current, or also called as the shunt field current. That shunt field current will increase now the flux produced by the magnet. So it will align further the magnetic particles and cause now to increase the flux, and at the same time the flux produced by the coil. So that increase of flux now will again cut by the conductors in the armature winding. That increase now the generated voltage from the residual voltage. So it will increase and so on. Okay, so that increase of voltage again applied to the shunt field, that will cause again to increase the field current. It will increase again the flux. So cumulative yung pag-increase ng voltage until such time that the desired voltage of the generator is already attained. So very important yung residual magnetism. So what are the reason behind why maybe the residual magnetism is lost? So maybe by time, okay? So if the generator is not used for a long period of time, there's a tendency that the residual magnetism is lost. So how could we regain the residual magnetism? So we're going to apply a DC voltage to the field winding for a maybe a few minutes or a few seconds, so that the magnetic particles will align. And if you're going to remove the uh, source na DC, then the magnetic particles will retain a small arrangement that will cause now the residual magnetism. And that method to regain the residual magnetism is called the flushing the field. Okay, so flushing the field is the method or procedure to regain its residual magnetism. Yeah, okay, so this flushing the field is we're going to disconnect the connection of the field winding. Then after that, we're going to apply a DC voltage for a few seconds. Then after that, we have now the residual magnetism. So that is number one condition. There must be a small voltage resulting from residual magnetism. None, then you cannot build up the output of the generator. Number two, the total field resistance as our reference. Let's say to illustrate now that one, using the magnetism curve. So I will draw another para makita natin. So let's say to draw the magnetism curve. Magnetism curve is curve generated between the field current IF and the generated voltage E. So that we have looks like this. Then after that, we will also draw the so-called Ohm's law line or excitation line. So this is the magnetization curve. So we already discussed how could we produce this. Next is we're going to draw the Ohm's law line or excitation line. The Ohm's law line or the excitation line is always start from the origin. And we will assume a voltage that is applied to the field current now, for that should be equal now to that voltage, E1 na lang, then divided by the resistance of the shunt field including the field rheostat. So, assuming that the voltage E1 is this one, so you can assume any value that is above the residual voltage. So, we have the residual voltage here, and there should be a corresponding field current for the say IF1. Okay, so assuming that the resulting field current for that given voltage should be this value IF1. So meron tayong point dito, so that if you connect now the origin to that point, will give to us the Ohm's law line or the excitation line. So we have here uh, Ohm's law or excitation line. So whatever the intersection of this line to the magnetization curve is called as the build-up voltage. So that is the output now of the generator. So if we're going to maybe increase the resistance of the field, what will happen to the position of the Ohm's law line? Say we're going to decrease the um, resistance. Sorry, in the other way around, okay? So we're going to increase the resistance of the shunt field. So what will happen is for the same voltage E1, so meron tayong IF2 by another value of resistance of the field, maybe RSH2, such that RSH2 is greater than the value of the shunt field resistance at condition 1. So what will happen to the field current should be decreases. So assuming the decrease now of the field current should be this much, we have IF2 here. So that if we're going to connect now the origin to that point by a straight line, then our curve should be looks like this. So that is almost coincide with the uh, lower part of the magnetization curve. And the intersection of this curve is this one. Ito yung build-up voltage, which is a low value, which is slightly higher than the residual voltage. So this is not considered as an output of. So if there's a tendency that the curve should be go here, okay? The Ohm's law line or the excitation line, and the intersection between this line to the magnetization curve is this one. So it will not build up. So what will happen is we're going to decrease the resistance until such time that the curve, just like the first curve that we draw. And the critical resistance of the field should be shown. So itong gawin ko lang na red para makita natin. So this line na red for the Ohm's law line will give to us the ang resistance natin dito, the shunt field is equal to the critical resistance. So itong tinatawag natin na critical resistance, such that we can compute that by considering any point in the between the curve, magnetization curve and the excitation line, that is, they are coincide. So any point here to determine the voltage and corresponding field current and take the ratio for that will give to us the critical resistance with this formula. So, yeah. So, in order to build up voltage, we're going to decrease the um, field resistance below from this one. So, either nandito yung curve natin, okay? So, we have curves here to come out with this different build up voltage. Ayan. So, it should be below the critical resistance. That is number 2 condition. So, the total field resistance, including field rheostat, must be less than a so-called critical resistance. So, very important yan, okay? Because if you're going to operate a generator that even you're going to drive now the armature with the required speed, then we have also the necessary magnetic lines of force, but the setting of the total resistance is maybe equal or greater than the critical resistance, then the output of the generator is a very low voltage. So it will not build up to its rated voltage. So ang gawin natin is we're going to decrease the field rheostat until such time that the value, the total resistance now of the field including the rheostat should be less than the so-called critical resistance. Okay, so that is number 2. Then how about number 3? The speed of the armature must be above a so-called critical speed. So if we're going to draw also the relationship, say to draw a curve for the speed and the generated voltage, it will looks like this. So this is for the speed, maybe in revolution per minute, and we have the generated voltage. So maybe the curve should be looks like this. So if the speed is maybe below from this one, so ito yung tinatawag natin na critical speed, that if you're going to operate the speed below this value, the generated voltage is low. But if you're going to operate now the voltage above to this, you will see here that the generated voltage now will abruptly increases. So that is for the relationship now of the speed. So we're going to operate the generator or the prime mover that is above the critical speed. That is number 3. Then number 4, there must be a proper relation between the direction of rotation and the connections of the field to the armature terminals. So again, let's try to illustrate this by diagram again. So let's try to consider again a two poles. So let's say to place the electromagnet. So we have the field winding. Then we're going to place also the armature windings. Then meron tayong output letter DC volts. Assuming that the residual magnetism will be north here and south here. So okay, let's try to draw also the schematic diagram of this. Then we have the output here, E. So assuming that the current now uh, flowing here, IF, or the shunt field current will be flowing like this, causing the polarity of the output to be positive here and negative here. So assuming with that direction na clockwise rotation, it will build up the voltage. So it will cause now that direction of the polarity and the direction of the current to come out with this output na plus minus. Then how about if we're going to um, reverse now the connection of the field? Say yung F1 should be connected now to the lower part. So we're going to connect here and this one should be connected there. So bale ma-disconnect yan so that is the connection. So what will happen is the direction now of the current that is flowing and the field winding should be reversed. So you can see in the diagram, so kung mag-reverse siya, the polarity that is produced by the um, field winding should be also reversed. Okay, so the initial direction should be south here and north at the right side. So what will happen is it will cancel out with the flux produced by the magnetic particles. So there's a time that the flux produced by the coil is the same as the residual magnetism, and the total now will be zero because they will cancel out its other. And if that is already zero, the flux now that is cut by the conductor is already zero, and the generated voltage is zero. So, yan. So kung um, there must be a proper relation of the rotation of the armature and the connection of the field winding with respect to the armature terminals. Same also, if we maintain the connection that F1 is connected to the upper portion and F2 is at the lower portion, but we're going to change the rotation of the armature, what will happen is the generated voltage of the armature will also reverse, causing again to reverse its current in the field winding, and the same arrangement as the first discussion that the flux produced by the coil is opposite to the initial flux in the core, which is the residual magnetism, and they will cancel out until such time that it will become zero if they are equal in magnitude. So if the flux now is zero, then the generated voltage now will become zero. So it will not build up. So number four condition is there must be a proper relation between the direction of rotation and the connections of the field to the armature terminals. So kailangan ma-meet natin lahat ito in order to build up voltage for a shunt generator. And the same also for the other type of generators. Say for series generator, and also compound generators. They are a self-excited generator. So if you meet these problems maybe later on, then you have already an idea how could you uh, correct now so that it will build up now the voltage of a DC generator. In the separately excited, there is no problem in the building up voltage because we excite now the field winding by another DC source, meaning it will already produce the necessary flux to be cut by the conductors in order to generate voltage and also power later on. But in the self-excited, so kailangan makapag-start siya by meeting all these conditions. So if you could not meet any of this, then you cannot build up any voltage in the generator. So those are the four conditions to be met in order to come out with a voltage in self-excited generators. Different conditions, and we will end up to this point. So we continue the discussion by solving problems next meeting.